how compilers work, right? That's much more interesting than how the massive machine works. But we need to know how the massive machine works in order to get anywhere near writing a compiler. The kinds of programs we want to be able to compile are programs like this. You'll notice that I have subtly extended IMP with the ability to describe functions. So here we are declaring a new function as a thing that returns integers. It's called GCD. It takes two parameters, x and y, and then it does this calculation by Euclid's algorithm to compute the greatest common divisor of its two inputs. And then we can use functions in expressions like to perform that calculation. So how do we go about turning this lot of symbols into something that actually runs on the massive machine? Well, I'm going to work a little bit at a time. So I've got the extended grammar. Better zoom out. Right, the point about showing you this is, well, that some things are exactly as they were. We've got integer expressions, we've got commands, we've got blocks, and all of that sort of stuff. So one of the things you have to do when you're writing a compiler is to communicate to the computer what is the syntax of the language that you are trying to compile. And in the system that I built for doing this, you communicate that syntax by directly writing down the grammar in the usual notation that we have been working with. So you just write down the grammar. But then, in order to explain how to turn something which parses in this syntax into executable code, you need to do a bit more work. And I'm going to do that more slowly if I can. You need to equip each syntactic category in the grammar with what is known as a compilation scheme. So here is the compilation scheme. Maybe I'll just use this as a crib sheet and develop it more slowly. What does a compilation scheme look like? Am I on the screen? Yes, I am. You say, so here I'm saying, I'm going to explain how to compile commands. So I'm declaring the compilation scheme. And then I say, what extra information do I need in order to compile a command? And I need two pieces of information. And it's not very revealing just to look at the types of the information. But I'll add some comments that are not part of the program, but they're crucial to the idea. In order to compile a command, I need to be told two things, and when I have compiled the command, I give back a piece of information. So what's an accessor? If we remember from last time, an accessor is one of these things which is which you can have on the right-hand side of an assignment It's a register or a value or some pointer to a bit of memory somewhere. In particular, it can be a memory address. So what we're going to give back is the address of the compiled code. Also known as the entry point. Our compiler for commands is going to generate some code, and it's going to tell us when it's finished the entry point to that code, so that if we want to actually run the command, we know where to jump to. Does that make sense? And here's a clue. The accessor we need in order to generate the compiled code for the command is the exit point. So if you give me a command and the memory address of what you want to do after the command, we should be able to put the whole thing together and give you the memory address of where to start. Sometimes the exit point is also referred to as a continuation. So you say, here's what the command is, and here's what I want you to do afterwards. Give me the entry point for the whole thing. And this number, which will be terribly important later, is called the frame height. It tells us how much local storage has already been allocated. Okay, so we have basically explained the syntax for invoking the compiler on a command and what extra information we require. However, when we're building a compiler, we need to be way more precise. We need to specify what assumptions we are making about the state of the machine when the compiled code starts executing, and what assumptions, what guarantees we're going to make about the state of the machine when it finishes. So in particular, we're going to assume that when the code starts executing, the frame height tells us how far the stack pointer is above the base pointer. So various things push the stack pointer above the base pointer. When we allocate memory on the stack for a new local variable, that will go above the base pointer, and the stack pointer will be above that. In particular, the frame height tells us where we expect, where relative to the base pointer we think the top of the stack is going to be, and we will make crucial use of it when we compile new. We're going to guarantee at the end exactly the same thing. That the stack pointer will still be in the same place when we give up, when we stop, as it was when we started. That's just tidiness, and we should also be explicit that we are going to make no promises about other registers. Okay, so we need to play this game for all of our syntactic categories. We'll do it a bit at a time. Let me at least do integer expressions now, because we're not going to get very far without them. So if we're compiling an integer expression, we will also need a frame height, an accessor, that's the exit point, and we're going to give back an accessor. And we have to document the deal, which is the same except that we promise value of expression ends up, and we have to choose where it's going to go. And we can pick anywhere we like, as long as we're consistent about it. I'm going to choose, because it's the obvious thing to choose, I'm going to choose the first register. Okay. So now let's figure out what we have to do is work through the grammars of all of our. So once we've established the way to invoke the compiler for all of the syntactic categories, we have to work through the grammar of each of these things and explain how every production in the grammar turns into a lump of code. Let's see if we can start doing that. So you can see here in my compiler for commands, maybe I'll not copy this out. We have an example of how to compile an assignment. And what happens? So this is how we invoke it. The command is x is assigned IE. We've got variables that stand for the syntactic subcomponents. So this x is a meta variable that stands for some program variable, and this IE is a meta variable that stands for the integer expression on the right-hand side of the assignment. H is our frame height, and end is our entry point. And what I'm allowed to do then is to say the entry point is going to be this thing called start, and then I say where, and then in some braces, in some curly braces, I do some code generation. Okay? So what I say is that the entry point start is going to be given by compiling the integer expression. We're going to need the code that evaluates the integer expression. So we compile the integer expression, we give it the same frame height, and we say your exit point is this label store. And then we write the label store, and we say what it is, what's going to happen after the integer expression. There's a built-in symbol table that allows us to look up variables and find out what accessor they are stored at. So this lookup x means tell me what place in the machine corresponds to the variable that x stands for. And since we got the promise from, since our deal was value of expression ends up in fi, we know that when we arrive at store, the value of the expression is going to be in fi. So the code that we need to give to do the assignment simply takes what's in fi and puts it into whatever the place that x represents. Yeah, it just does that assignment. And then we finish our code block with this arrow pointing to, we say, where we're going to exit. So it's always a bunch of things in the braces separated by semicolons, finishing with a where to go next arrow. And each thing in the braces is either a call to another compiler or it's a label and some actual assembly language. So you can see here we called the compiler to compile the expression. We were promised that the value would end up in the first register, so the code we need to do next is just a single move of the value from where it is to where we want it, and then we can exit via the exit point we were asked for. So a lot of the time you'll see this happen, that we take an exit point as a parameter, and that is indeed the place we end up going to once we've done all the necessary things. Okay, let's look at some more. We can say what the deal for a block of commands is. Actually, the deal for a block of commands is exactly the same as the deal for a single command. So let's see if we can figure out how to compile a block of commands. If somebody gives us the empty command, the empty block with frame height h and exit point end, what should we give back as the entry point?
End.
Exactly. There is nothing to do between now and going to the exit. Okay? If somebody gives us a command and some more commands, frame height h, exit point end, now we're going to have to do some work. So we start, well, there's going to be an entry point, which I'm going to call start, and what start is will appear in a moment. And then I'm going to write one of these code blocks. In order to execute C semicolon C's, what's the first thing we need to do? Well, one command comes before the other ones, right? So we're going to need to make sure that we do C first. So I'm going to say that start is the, remember, a compiler returns the entry point of the generated code. So I can just say start is the entry point we get when we compile C. I'm going to give, well, the frame height, we haven't done anything to the stack since we started. So I can give the same frame height. What exit point should I give? Well, we don't want to give end here because we haven't done the other commands yet. So we better make up a label. And then define what's at that label. What's at that label is going to be the code generated by compiling C's. Now, do we know what the frame height is at this point? Check the deal. We were promised that the code generated by a command would leave the frame height as it found it. Correspondingly, we are entitled to give h as the frame height for the next block of code. And if we were not being given that promise, we wouldn't have a clue what to write here. That's why the invariants are mission critical. Now, what shall we give as the exit point for this compilation? He says, staring at his notes. Any suggestion for the exit point? This page is sort of around the order. Well, I think I'm just trying to remember what I actually wrote back in the day. In case I'm going to write something that makes sense morally, but does it actually make sense in this programming language? And of course, there's inevitably a page missing. Right. What are we going to do after this lot? What do we give as the exit point for the rest of the commands? Well, I am entitled here just to stick in end. So that's to say, we compile C then C's by saying, we start by saying, the entry point is where we put the code that corresponds to C. We give it as an exit point, a label for what to do next, and we say next is the entry point for the code we get when we compile the rest. And that the rest of the stuff should exit in the place that we actually wanted to exit from the whole thing. Is this making a reasonable amount of sense? Okay, good. Let's do a more complicated one. I think I'll need a whole fresh piece of paper for this. Let's do the new command. So we're going to compile new x is assigned IE in command CM, stack frame height h, exit point end. And that's going to be start, and then we get to define a bunch of stuff. When we are computing a new, what is the first thing we need to do? Sorry?
Figure out where to start the value?
We haven't got the value yet. Yeah, get the value, right? So that means the first thing we need to do is generate the code that corresponds to IE. We haven't monkeyed around with the stack yet, so we can give frame height h, and exit point will be something, I'll just give it a name, I'm actually going to call it push. Okay. according to the deal, the value of the expression is now in the first register, and the frame height is still h. We need to now allocate some storage that corresponds to the variable x. And that's what we use the stack for. So we start by saying, wherever the stack pointer is pointing, please copy the contents of the first register there. So now we have stored the value we just computed on the stack. Of course, if we want that value not to be overwritten by the next new variable that comes along, we had better move the stack pointer up by 1. And then we are ready to do the actual command. And here's where, so this is a little assembly language code block. An assembly language code block always ends up with an arrow and an exit point. And now I can define body, and that is going to be the code that corresponds to executing CM. But there's an extra thing I have to do. The compiler needs to know what accessor to use whenever we look up x. So I have to tell it to extend its symbol table with the right way to find the value of x. What accessor is the translation of x? My notation for that, I'll actually switch color because it's important, is I just write a set of curly braces with x arrow. That means the curly braces means extend the symbol table with a translation for x mapping to, and then I write some accessor. And we just said that x lives on the stack. The stack pointer wanders around all over the place. The base pointer does not. So we can express an accessor for x in terms of the base pointer. Where is x relative to the base pointer? Well, where the stack pointer was at the start of the code block, that's where we put x. So what's that location in terms of the base pointer?
H.
It's BP plus h. That's why we keep the frame height, so that we can translate an address in terms of the stack pointer into an address in terms of the base pointer, because the base pointer doesn't move. So we know that whenever this command refers to x, no matter what it's done with the stack, the value of x will still be in this place, in this location, BP plus the h that we were given here. Now, when we invoke the compiler for this command, what should we give as the frame height?
SP minus PP.
and we know what that's going to be. You're right. But the compiler doesn't know. The compiler can't see what's in the registers of the machine that will run the program in the future. Right? We need to know now what the frame height is. Well, before we did this increment on the stack pointer, the frame height was h. What is the frame height now? H plus 1. And then we have to give an exit point. Now when the command is done, are we done? He says, wondering how close we are to being done with this lecture. If I write end here, it's true, there's no more computation to be done after this command is finished. But I'm breaking an important part of the deal. I have to guarantee at the end that the frame height is what it was when we started. That the stack pointer minus base pointer is still h by the time this command finishes. So I have to tidy up afterwards. I'll give as an exit point pop. And then what does my code at pop do? All it does is decrement the stack pointer. And now we can go to the exit. Do you see what's going on there? We had to work through the deal very carefully to make sure that we chose the right frame height to account for the fact that we had allocated a bit of extra stack to store X, and we had to extend the symbol table so that the compiler knows how to compile references to X. And you can see that exactly the same things that were going on when we wrote the dynamic semantics as a bunch of rules are happening here. This move here, the push move, exactly corresponds to X being added to the store in the premise for the command when executing the new rule, and this pop corresponds to the store no longer having that thing in it when we give it back at the end. So the same things that happen in theory in the dynamic semantics, you're seeing them turning directly into assembly language instructions here. Okay, I think we have time for one more. Let's do plus. How do we compile IE1 plus IE2 with a frame height and an exit point? Well, we've got to start somewhere. What is the first thing we need to do if we're trying to add the values of those two expressions? How do we start?
IE1.
We need the value of IE1, so we better start by compiling IE1. That start is going to be the entry point for that code. And we haven't done anything to the stack, so we can give the same frame height. And then we need to figure out what to do next. what's next? Well, first of all, where is the value of IE1? What was the deal? Value of expression ends up in first register. So what is the next thing we should do? Well, if we plow straight into running the code for IE2, where's that going to put its value? In the first register. So where's the old one going to be?
Overwritten.
Exactly. So before we start with the code to compute the value of IE2, we had better put the value of IE1 somewhere safe. Where shall we put it? You could think, well, you know, we've got a few extra registers, we could just bung it in some other register, but that's a trick you can play once. And remember, the deal says we make no promises about other registers. So it's not safe to store code, or to store that value in a register. We had better put it on the stack. So you've seen this move before. We put it on the stack. And we increment the stack pointer. And now we're ready to run the code for IE2. And I'm going to run out of names, so let's just call it second. Second is going to be the entry point for IE2. What shall I give as the frame height? We've been through this movie before. I just saved something on the stack. 8 plus 1. And then there's going to have to be some tidying up code. Well, actually, we're going to have to do the calculation. So let's call this ready. Okay. So by the time we reach ready, the value of IE1 will be still on the stack. The value of IE2 will be in the first register. We also have to restore the invariant. We have to make sure that we pop the stack. So let's start by popping the stack. So the stack pointer is exactly as it was when we saved the value of IE1. So the same accessor should work. We are now ready to do the actual arithmetic. That is where the value of IE1 is. That is where the value of IE2 is. The arithmetic instruction will perform that calculation, and it will very conveniently put the resulting value in the first register, which, now we come to mention it, is exactly where we want it to be. So, have we kept the deal? Is the frame height, is the stack pointer back to being h above base pointer? Yes. Is the right answer in the first register? Yes. We may then proceed to the exit. And that actually looks like a good, got to close my curly brace. Okay, so what happens? You basically do this for every construct where you can get the code for the substructures, and you can write these little code fragments and you string them together. So far we've done only straight line code. Actually, maybe I do just have time to do if. Let's do if. How do we compile if BE CM no else CM1 well, first of all, I have to tell you what the deal is for Boolean expressions. We have to decide what the deal is going to be for Boolean expressions. So it's going to be the same sort of thing. It's still going to take a frame height and an exit point and give back an entry point. It's going to make all the same promises as commands. But where should it actually return the Boolean value? Well, I think it would be terribly convenient if it promised to ensure that the flag told us the Boolean value. So the deal is that a Boolean expression will set the flag if the value of the expression is true and clear the flag if the value of the expression is false. So to the person who asks, are there Boolean constants in the massive machine? Well, there are instructions which test things that are always true, and there are instructions that test things which are always false. You can ask, is 0, 0? You can ask, is 0 not 0? And that way guarantee either to set the flag or to clear the flag. So that's the equivalent of Boolean constants. All right, so how do we start? I think we better start by testing the conditions. So we want the code that corresponds to the Boolean expression, same frame height. And what we're going to do next is some code at this location branch. Okay. So how do we branch? Well, first of all, we need to say, if the flag is true, we want to go to the code that that executes the then case. It's actually rather weird. I should call that 1 and that 0, because that's the code that is executed if we get a 1, and that's the code that's executed if we get a 0. How about that? Okay, so conditionally, we set the instruction pointer to the code that does 1. And I have to come good on, so that's just a label, I have to put something there in a moment. Otherwise, we say the exit point of this code block is do 0. But now I have to define do 1, well, do 0 and do 1. Do 0 is going to be the entry point of the code that executes CM0. Frame height, nothing's been happening on the stack. We can give back frame height h. Remember, we are promised that evaluating the Boolean expression won't knacker the frame height. And what should we do after we've finished executing that command in the else case? We know where we want to end up after the whole if. If we've decided we're executing the else branch, then we want to end up there. So we can just stick end in there. Same deal. Do1 is the code generated for CM1, frame height, end. So that's how you compile a conditional, how you compile if. You ensure that the Boolean expression will set the flag if the Boolean's true, clear it if it's false, and then if the flag is true, you jump to the code that does the true branch. Otherwise, you say, I want to carry on with the code that executes the else branch, the false branch. So, if that's how if works, then it's the usual cliffhanger. Why don't you have a wee think about how while is going to work, and I'll tell you next time.